So last time we derived the second quantization for single particle operator in many body system. And remember, we defined this occupation number operator to count this particle number. And for fermion or electron systems, we can simply just count this electron number and multiply by the kinetic energy per electron. And also, we can actually derive this single particle potential out of a many body system. So today we will generalize this second quantization approach to two particle operators. Namely, the most important interaction in solid state is the Coulomb interaction. And the Coulomb interaction is a two-body interaction. So remember, we estimated this T square of a resistivity for ordinary metals in low temperatures, and we argued that two electrons come in and they get scattered out, and so we need to calculate this phase space, the probability that the two electrons can actually get scattered by Coulomb. So now we officially define such a operator in a second quantized form, but we need to start from the very beginning. And by using this occupation number basis and mu, remember that we could define the occupation for any quantum state, whether there's a particle or there's no particle. And in terms of this occupation basis, we could calculate the matrix element of this two-body interactions in terms of many-body wave functions. Remember, this many-body wave function, phi or phi star, is nothing but the product of many single particle wave functions, right? So this alpha 1 to alpha n represents all the single particle states at position R1, R2 to Rn, and they carry this quantum number A, B, up to Z. And on the right side of this integral, is the same. And then we need to integrate over all this real space vector R1 to Rn in order to get this matrix element. So that's first quantization in quantum mechanics. Okay, but we know that those single particle eigenbases, say UA and UA prime, are normalized and orthogonal eigenfunctions for a single particle eigenstate, so they should satisfy orthonormal conditions that if we calculate this overlap between UA and UA prime and integrate over this R1, so they are both for a particular particle in R1, and that integral should become a Kronecker delta function, delta AA prime, which means that this is 1 if A, or this quantum number, or this labeling for this quantum state is the same as A prime, and 0 otherwise. So this orthonormal condition is very useful, because you can see that this matrix element for these two-body interactions, like I plotted here, we have two incoming particles carrying quantum number gamma and delta, and they get destroyed, and then two new particles carrying quantum number alpha and beta are created. Okay, so we should be able to describe such a processes using this first quantization or in quantum mechanics, but then we can rewrite this in terms of the second quantized fields, operators. Remember, these particles are located at different real space position. So even though they carry different quantum numbers, but there are only two sites involving, namely Ri and Rj. So there is a particle here at position I and another and J, and they interact by Coulomb. So when they get scattered, the ith particle is still in the ith position, and the j is still in the j position. There's no mixing and no hopping. And so you can see very clearly that there are only 4 states that depend on the interaction. So these are the 4 states, U, R, I, and U, R, J, with alpha, beta, and U, R, I, and U, R, J, and gamma, delta. So there are only 2 sites that connect to the interaction, and all the other single particle wave functions don't get involved in this potential. Okay, and therefore we can only pick 4 states, 2 initial and 2 final states wave functions, and then forget about all the others. Okay, because of the orthonormal conditions, and all the other single particle wave functions could be decoupled from this integral, and then they become something like this. And we could do that by simply just extract all the other irrelevant, say, wave functions, and when they get together, so you have this precise integral that we mentioned here, which gives you delta function, right? So there are a bunch of delta functions. Okay, delta AA prime, delta BB prime, and so on and so forth. But we need to take special care of the 4 states, alpha, beta, gamma, delta, states where these single electrons are either at side I or side J, and they interact by Coulomb. Okay, so this is the only 4 states that we should worry about. All the other states are gone because of the orthonormal conditions over there, right? So then we should simply just focus on this 4 states, 2 initial and 2 final, and they interact by Coulomb or some 2-particle interaction. So then we could simply just rewrite this operator in terms of, again, occupation number states, and with 2 initial and 2 final occupation. For initial states, we got n gamma j and delta I singly occupied, with occupation number being 1, and the final state's occupation are 0. Okay, so that's the initial state, and the final state is the same. But the other way around, so the 2 initial states are empty, but the 2 final states, have a single occupied, particle. Then we could simply just rewrite this operator V in terms of such initial and final state in the Dirac notation. And like we defined earlier for the single particle creation destruction operator, we can define, destruction of 2 particles, gamma and delta, and creating the 2 new particles, alpha and beta. And of course, the matrix element V alpha, beta, gamma, delta is precisely this stuff over here. So this is the matrix element. Okay, so the matrix element is nothing but the overlap integral between 2 initial and final, and also this interaction potential. Okay, so this is the second quantized form of a 2-particle potential, that we destroy the 2 initial states or 2 particles initially, and then we create a new particles afterwards. Right? So it involves 4 operators, 2 daggers and 2 non-daggers. So the 2 non-daggers are destruction operators, and the 2 daggers are creation operators. Everything is really the same for a single particle operator, except that now we have double the number of operators. So it becomes messy. And in most cases, we cannot solve this operator or the eigenvalue equation for this potential operator, 2-particle interaction exactly. So there's no way that we can solve this exactly in general, but we can make approximations, and we would discuss how we make the approximations. For example, this Hartree-Fock is one way to make approximations, and there are other ways to deal with this messy operators. Right? Everything just follow what we did before, except now we add one more particle in the game. Okay? There are 2 particles involving, and therefore there are 4 states. That's all. And 1/2 here is just guaranteed. There's no double counting when you count this potential energy. So the sum is for all the I and J's that are not equal. So now let's do a very simple algebra to check this kind of a second quantized form of the two particle interactions. And this is kind of a trivial task, but when we use this anti-commutation rules for, say, electron operators, and this calculation becomes non-trivial. Okay, so let's see if this potential VRI minus RJ is simply just a constant or 1, number 1. Okay, so that's really trivial because now the energy, potential energy becomes this summation, which is 1/2 of sum over I and J. R is not the same as J, and inside the summation is just 1. And from your high school mathematics, you know that this is n times n minus 1. So that's trivial. But the highly non-trivial thing is that how about we calculate this number from this operator formulas then? Okay? Can we do that? Can we check whether this V is actually the same as this value? But we don't just do this. It's just trivial. But we do this non-trivial way. So we simply sum over alpha, beta, gamma, delta, and this operator here. Okay? So this is a real non-trivial test for this anti-commutation rules, which will recover the simple and naive looking innocent result. So let's just do it. Before we sum over this 4 indices, let's just calculate matrix element V alpha, beta, gamma, delta, and we plug in this, the formula over there, and we know that this potential energy or interaction strength is just a constant 1, and therefore the matrix element V alpha, beta, gamma, delta is nothing but the overlap integral between these two initial and final states. And because of this orthonormal conditions here, we simply just plug in this orthonormal. We got 2 delta functions. So delta alpha and delta and beta and gamma, they should have the same indices because these 2 wave functions describe the same particle in the same position, right? Okay, R1, and the middle ones describe this particle at R2. Okay, so you should pair 1 and 4 and 2 and 3, not the other way around. Okay, so if you pair them up and you get 1 delta, if you pair up this middle 2, you get another delta function. So now let's just plug in these 2 delta functions back to the operator form, and let's see what happens. Okay, so this is what we need to do. So there are 4 summations, but there are 2 delta functions, so which means that you could get rid of 2 of these summations by using these 2 delta functions. So suppose I get rid of 1 of the summations, say delta, by summing over delta, and delta should be alpha. So this is alpha. And I can get rid of, say, gamma by summing over the gamma, and gamma should be beta. And that's it. Okay? So now the summation reduces 2 indices, alpha and beta, and inside the summation you get these 4 operators, C dagger alpha, C dagger beta, C beta, C alpha. So now we could take advantage of this anti-commutation rules for fermion operators. Remember that C alpha and C beta, they anti-commute. C dagger alpha, C dagger beta, but C alpha and C dagger beta is actually delta alpha beta. Right? So this is the anti-commutation rules, and so now we could use this anti-commutation rules to rewrite this summations. For example, you could simply just interchange these 2. Suppose I interchange C beta and C alpha, and I should use this anti-commutation rules, C alpha C beta plus C beta C alpha is 0, so that C beta C alpha is just minus C alpha C beta, right? And this is minus C delta alpha beta C alpha C beta, right? See that? A minus sign. So now let's just replace this middle two operators, by using the anti-commutation rules for C and C dagger. So this is given by this C dagger alpha and C alpha C dagger beta minus delta alpha beta and C beta, right? So I simply just rewrite this in terms of the other way by using this anti-commutation rules. So now let's just, there are two terms up to here, and so we can simply just sum over this alpha and beta for these two terms. So let me just write it here, sum over beta C delta alpha C delta beta C beta minus delta alpha C alpha. Okay, I can simply just, spell out those two terms and sum over alpha and beta for each of these two terms separately, right? So let's just sum over the first term. So what do you see for these four operators? So these four operators are in the perfect ordering because I can define this occupation number operator. Remember that C dagger alpha C alpha is nothing but the number operator for the states alpha, and likewise I can define an operator for beta. What is the meaning of this n alpha hat and beta hat? This is nothing but this occupation number operator, which takes this eigenvalue as an occupation for this particle staying in that state, alpha or beta, and the remaining term is simply just n alpha wearing a hat. So this is nothing but 1/2 of sum over alpha beta and n alpha times n beta minus 1. Okay, so sounds familiar. So when you sum over alpha and beta, you get total number of the occupation, which is exactly this value over here. Checked. Sounds simple, but not that simple. Sounds trivial, but not that trivial. Because in order to go back to this trivial, simple results, you need to apply this anti-commutation rules many, many times when you actually interchange these operators. And when you do this correctly, you should be able to recover this, naive counting of a particle number. And this is the power of a second quantization, because in this trivial case, we could recover this trivial answer. But suppose this potential is not that trivial. Suppose this is complicated operator, then there's no way that you can simply just do that power counting with a trivial approach. But still, we are able to count the particle or calculate the potential, the matrix element potential operator in a second quantized form. So this is always a way, but the simple counting may not work in general. But this second quantized method always works. So the power of the second quantization, and we could take advantage of such a nice property of the second quantized fields and their anti-commutation rules for fermions, and then we could define those interactions either in real space or in K-space, which we'll discuss in just a moment. So let's take a short break. When we come back, we will continue describing the Fourier transformation between the real space operator and K-space operator. And then we will come back to this Coulomb interaction one once we define such Fourier transformations, and later we will address this real problem of the Coulomb interactions. So this is our next job. Okay, suppose we have this 1/r potential between two fermions, and what is the potential energy when we sum over all different electron pairs. So far, we find a way to create or destroy a single particle in, say, k-space or real space, but we haven't defined properly the operators which destroy the particle in real space. And we will do that just now. And then the creation or destruction of a particle in real space and k-space are linked by the Fourier transformation. And that is also important to know. Okay, so then that's the topic now. So we could either define C dagger C in real space or k-space, but we need to be careful when we define these operators in either basis, and they have Fourier relations, right, with each other. And then this anti-commutation rules are satisfied in both cases. And then depending on the nature of the problem, sometimes it's easier to define these operators in real space, but sometimes in k-space. So, and that's why we need to really define these operators in both cases. So let's discuss this basis transformation. We can define this creating particle in real space, but we can also define a creation of a particle in k-space. And there is a relation between the two, which is a Fourier transformation. But let's just put it in more general form that we could define a single particle states in k-space. But I just put it in mu to represent that this is in some basis. And in my mind, this mu denotes this momentum state, momentum basis. But this could be expanded in terms of another orthonormal basis, which I call this nu, from quantum mechanics. So any quantum states could be expanded in terms of any other orthonormal basis functions. And I could choose whatever I want to expand that arbitrary quantum states in terms of whatever I want eigenbasis. And this, the new eigenbasis that I expanded this about is called nu. But in my mind, this nu represents real space eigenbasis. Okay? But you could interchange these definitions you like. So then we could simply just rewrite this expansion in terms of this matrix element. So secretly, I represent this psi nu as some single particle in position r. And secretly, this is a single particle in momentum state k. Okay, so that's, I'm the only one who knows this. Okay, so I have the freedom to choose the spaces. And therefore, we could actually define a new kind of an operator, a mu theta dagger, which is sum of a nu phi mu psi nu star a dagger nu. Likewise, a theta mu is actually sum over nu phi mu psi nu a nu. For operators defined in the mu space, I put it theta. Okay. For operators defined in the nu space, I don't put a theta here. Okay. So you could just call this what? C dagger k, and this is ck secretly. Don't tell anyone. Okay. And this is what? Psi of r dagger, and this is psi of r. So in other words, if you create or destroy a particle, single particle in momentum space k, and you could rewrite this operator in terms of the Fourier series of the creation or destruction of a single particle in real space and multiply by this Fourier coefficient. So we will explicitly rewrite these identities in R and K space respectively. But in general, this don't necessarily imply this real space, momentum space. This could be arbitrary basis. So mu and nu basis could be arbitrary basis, okay? Angular momentum basis and whatever you name it, okay? But this relations holds for arbitrary eigenbases, mu and nu. So now let's just check this anti-commutation rules for this new operators in new bases. Suppose I consider these operators as fermion operators, and I define these operators in momentum space, k or mu here, and I would like to show that this is still the same as before, which is the same as this a mu1 and mu2. In other words, suppose we know the operators defined in, suppose this is a mu1 and a dagger mu2, delta mu1, mu2, then we could prove that this theta operator satisfies the same anti-commutation rules. So let's just do the algebra. This is sum over mu1 and mu2 by mu1 psi mu1 phi mu2 psi mu2 star a mu1 a mu2 dagger. So let me just remove that, and I should use that to more precisely link this relation between the anti-commutation rules in the nu space and those operators in the mu space. And the anti-commutation rules in nu space is none, which is delta mu1 and mu2. Therefore, we could just rewrite this 2 by mu2 delta mu1 and mu2. And we can sum over one of this nu, say nu2, by using this delta function here, and therefore the summation is just for nu1, and therefore recover the correct commutation or anti-commutation rules for the theta operators defined in the space mu. And this is not surprising because, as I mentioned, both eigenbases mu and nu are also normal eigenbases, and therefore the commutation rules and anti-commutation rules are perfectly satisfied in both spaces. Okay, so but we need to show that first. So we could safely use the operators either defined in real space or momentum space because the anti-commutation rules are valid in both cases. So that's the important lesson. And also, the total particle number should be conserved in either case. Total particle number. So let's check whether this is the case. So the total number in this mu or theta basis is defined as this sum over mu a theta dagger mu a theta mu, and we will see that this is the same as your sum over nu a dagger nu a nu. In other words, when you count this particle number and you sum over all the particle number in either mu space or nu space, you get the same value. So the particle number is actually the same regardless your basis. So, which means that I can count the particle number in real space, or I can count them in momentum space. Okay, but the total number of particles in real space representation, the momentum space representation should be the same. But this is not trivial. We need to show that. So we need to prove this. Let's just prove this. Again, we apply this Fourier decomposition between this theta and non-theta operators, and we could get this equation here. And we could simply just, simplify this, because this is nothing but the identity operator, right? So this is nothing but the identity operator. So we can get rid of the identity operator whenever we want. And the remaining summation is just for nu1 and nu2, and with matrix element and operator like this. So again, we have this orthonormal conditions for this overlap between this psi nu1 and psi nu2. This is nothing but delta function. So you plug in this delta function and sum over 1 over the nu, and you get the only summation over nu. So I can call this nu1, nu, or nu2, nu, whatever I call this. You can call this nu1 you like. Nu, a dagger, nu, a nu. So checked, because this is the total number of particle in the nu basis, and this is the total number of particle in the mu basis. So they should be identical, and they are indeed identical. Okay, so that's precisely because of this Fourier transformation. It's kind of an orthonormal transformations. It's kind of a coordinate transformation, so that all the nice properties in one space holds in another space. Okay, good. So let's take a short break. When we come back, we could finally define the creation operator for a single particle in real space. So we could finally define this. Okay, so let's continue. We finally are able to define the second quantized field operators in real space and in K-space, especially in real space. So let's just define this operator psi dagger of R, which represents the creation of a single, say, fermion in real space. So we follow the same definition that we define as creation operator by destroying the empty states or vacuum and creating a single particle state in position R. Okay, so that's the same way that we define the creation operator. But now the eigenbasis in the real space eigenbasis. So likewise, we can define the destruction of a single fermions in real space R by destroying the single particle Bragg state R and creating an empty state or vacuum. So that's just psi of R. But we know that we could Fourier transform this to the K-space representation A dagger A with a different basis called nu, and this nu, I define this as momentum eigenstate, and the coefficient is called psi star of nu as function of R, and in the summation we have this A dagger nu. Okay, so this A dagger nu could be just destroying the empty state and create a momentum single particle state K. So likewise, I could rewrite this destruction of a single fermion operating in real space in terms of a Fourier expansion of this single particle destruction in momentum space with a proper coefficient or expansion Fourier coefficient psi nu. So remember, this psi star nu as function of R and psi nu as function of R are precisely the Schrödinger wave function in this first quantization, quantum mechanics. So I think this is also a good homework exercise. Prove this statement. Okay. Show that these two functions are nothing but the Schrödinger wave function in the first quantization, quantum mechanics. Okay, so you need to go back to your quantum mechanics 1 and to actually, remind yourself what is the definition of this Schrödinger wave function in the Dirac notation, right? So this is nothing but this or that. So whatever convention you use, it doesn't matter, but okay. So if you project your quantum state psi onto the real space eigenbasis R, and you get the Schrödinger wave function. And likewise, if you do the reverse, you get the complex conjugate of that Schrödinger wave function. So this homework, is kind of a review of your quantum mechanics, but in particular the Dirac notation. Okay, so the only technique that we use so far is just the Dirac notation, nothing more. And the matrix representation of the operator, and everything else follows from this Dirac notation and the matrix form of the operator. And there's a second homework assigned to you, is to show that the anti-commutation rules for this psi of r or psi deg of r follow exactly the same anti-commutation rule. But pay attention to this delta function here. So this is a Dirac delta function. So as I defined already, this Dirac delta function is a sharp peak when this argument vanishes. So this is delta of x 0. But the Kronecker delta function, delta a b, is actually a step function, 1 or 0. So this is Dirac delta function. So when we perform the Fourier transformation, in K-space, this anti-commutation rules are in the form of a Kronecker delta function, namely this 1 or 0 type of delta function. But if we go back to the real space, and this Kronecker delta function becomes a Dirac delta function, where you really have this divergence when this argument inside the bracket vanishes. Okay, is infinity or 0, not 1 or 0. Okay, so you should distinguish these two delta functions now. Okay, so one is a step function, another is really infinity or 0. Okay, so and the only non-trivial properties here is that you should reproduce this Dirac delta function, okay, by Fourier transforming the operators in K space to the real space, and this Dirac delta function appears. So there are two homeworks. Okay? It's just simple algebra. So now we could officially perform such a Fourier transformation to link these real space operators and the K space operators. So psi dagger of r could be Fourier expanded in terms of the A dagger of K, where K represents momentum eigenbasis. And likewise, this psi of r destruction operator for a single fermion could be expanded in the inverse Fourier transformation. So whether this is plus or minus doesn't matter. You just keep your notation consistent. That's all. You could use plus here, minus here, and so on. Okay, it doesn't matter. And this 1 over square root of volume is just a normalization of this Fourier sum. So likewise, you could inverse Fourier transform this A dagger K or AK in terms of the real space operators, psi dagger and psi. And if you do so, then you could show that this anti-commutation rules satisfy, and AK, A dagger K prime. So now this is Kronecker delta function. So now we could easily, straightforwardly transform our operators either in real space or in momentum space by such Fourier transformations. Therefore, we can take advantage of such a kind of definition, and you could easily just rewrite this anti-symmetrize many fermion wave functions in different positions, R1 to Rn, and you could sort of rewrite this in terms of the creation operators. So sometimes they use C or C dagger in both K-space operators and real space operators. So let's just do this. So this is nothing but C dagger nu and 1, C dagger nu and 2, C dagger nu and n tau 0. So the first line is the many-body wave function for fermions in the first quantization. So in quantum mechanics, if you know the wave function of many electrons, and you simply just anti-symmetrize all the single fermion wave function, and you get this many fermion wave function. But in second quantized formalism, you can simply just use the creation operator C dagger to create such a single particle state, right? In other words, you don't worry about this anti-symmetrization of this, say, many fermion wave functions, because the C and C dagger automatically satisfy this anti-commutation rules. So that no need anymore, not needed. Okay, so we will use that second quantized fields always, okay, all the time in the later discussions. So, and Hamiltonian for a solid-state system could be expressed in terms of either the real space operators or the momentum space operators. So, whichever is more convenient. So, there's no strict rules that you should or you should not express your Hamiltonian in terms of real space operators or momentum space operators, just as I like. And you could check the commutation rules between the number operators and the creation or destruction operator. And you could verify that. And it doesn't depend on the, it is in real space or in momentum space. It should be the same. And I assign this to you as another homework problem. Suppose we define the number operators in eigenbasis nu. You consider this as a momentum eigenbasis or a position eigenbasis. Doesn't matter. But once we have defined the C dagger nu C nu as a number operator, then you could verify by using this anti-commutation rules that this the commutator between this number operator and the destruction operators is nothing but minus this destruction operators. And for the creation, this is a plus creation operator. So this is a very important relation to link the number operators and destruction and creation operators in the commutation rules. Okay, so we will take advantage of such identity over and over and over again in the later part of the calculation. So you could remind yourself the similar commutation rules when you study simple harmonic oscillator in quantum mechanics. So this commutator or commutation relations are very similar to the commutation relations that you found or studied in quantum mechanics regarding the harmonic oscillator. So using this anti-commutation rules, you could easily, straightforwardly prove that this commutation rules satisfied. So let's just continue. Let's link the kinetic energy of electrons in real space and in K space. And we call this K operators. So we know very well that they, this kinetic energy for a single electron in a single particle of the many particle systems is written in terms of the kinetic energy operator, sum over K, the kinetic energy per electrons, and the occupation number for that electron. Sometimes I use A, sometimes I use C, so I'm sorry for this kind of a little bit inconsistent notations, because our textbook uses A, so sometimes it follows. But the standard definition for electron operator is actually C. Remember that, okay? So now I can Fourier transform this A dagger K to real space, and I can check whether this formalism agrees with our Schrödinger picture. And let's do this Fourier transformation. So this is given by 1 over volume, dr1, dr2, sum over K, I k dot r1 minus I k dot r2 and psi dagger of r1 psi of r2. Okay, so we can simply just Fourier transform this A dagger K to the real space operators psi dagger psi, and we perform this integral. And this integral is easy to do because this is nothing but some delta functions. Sum over K e to the I k dot r1 minus r2 and psi dagger of r1 minus h bar gradient square 2 over 2m psi of r2. You can rewrite this line in terms of this, combined exponential factor, and you can rewrite this k squared in terms of the gradient operator. Gradient square acting on the right side part of your operator. Imagine this is just a wave function, but we will see that this is consistent with the Schrödinger picture. And you could just do this summation over k, and this is nothing but Dirac delta function, delta R1 minus R2, right? Of course, there's a volume here. And you can get rid of one of this integral, the R1 and the R2, by taking advantage of this Dirac delta function. So once you down that, you get just a single integral over the R psi dagger of R minus h bar square gradient square over 2m psi of R. You see, this second quantized form of a kinetic energy looks very similar to what you know in quantum mechanics, right? Suppose that psi dagger of R is just a Schrödinger wave function psi star of R, and psi hat of R is just the psi of R, and this is the same as the Schrödinger picture when we compute this kinetic energy. So let's just try to show that this is an equivalent description. Suppose this is my kinetic energy operator in real space representation, and what I want to do is just to evaluate this excitation value of the kinetic energy operator by projecting this onto this real space eigenbasis R, the Dirac-Broadbent state. And you should always remember that in the Schrödinger picture and Dirac notation, this is your wave function psi of R. By projecting your quantum state psi onto the Dirac-Broad state of a position eigenbasis, and your psi of star is the opposite projection. Do you remember that? And taking advantage of such identity in quantum mechanics, you can very easily show that this real space operator to express the kinetic energy operator is going to give you exactly the same results when you follow this Schrödinger picture. So let's do it. So if I project this kinetic energy operator, by sandwiching them between this Dirac-Broad state in, say, real space eigenbasis, and what I get is this integral. So I can insert this identity matrix 0, 0 whenever I want. So what is this? Psi star of R. And this is the kinetic energy operator, but then this is psi of R. So if you plug in this definition here, and I could just interchange this definition so that it agrees with our convention in quantum mechanics. So what is this? This is nothing but the kinetic energy of a single particle in quantum mechanics. If I know the Schrödinger wave function for that single particle, and this is the excitation value of that kinetic energy of that single particle. But I can rewrite this in terms of the second quantized operator, k wearing a hat, where this expression value of that k wearing a hat is nothing but the expression value of the kinetic energy that you found in quantum mechanics. So this is the link between the first quantization and the second quantization. Okay, so we are not inventing any fancy physics. It's nothing but rewriting, re-expressing the Schrödinger picture by using Dirac notation, and then we can rewrite this in terms of a newly defined second quantized fields. And when we evaluate this excitation value of such an operator, so it should reduces to what we are familiar with in quantum mechanics. This was a homework problem last year or even several years ago, but I already told you the answer, okay? So you could play this kind of algebra at home. Let me emphasize millions of times. Get familiarized with Dirac notation and Schrödinger picture in quantum mechanics. So that's the key that you should really be prepared in order to really understand the second quantization. So you need to review the Dirac notation in Schrödinger quantum mechanics, and then you will understand much better. So let me just comment on the benefit to use this second quantization. So why is the second quantization convenient? So as I already told you that we could count the particle number by this occupation number operators and by rewriting this Hamiltonian in terms of the number operators. But let me just more explicitly elaborate these reasons. Remember, in the single electron non-interacting limit, we have this kinetic energy, where mu is a chemical potential for some electrons. We will come back to this later, but let me just show you the convenience to use the second quantized fields to actually study some simple Hamiltonian in solid states, especially the free electron system. Suppose this is a free electron. And we know very well that if you evaluate this occupation number operator, say in K space, you will get a number which is nothing but the occupation number. And this occupation number is nothing but the Fermi-Dirac distribution if the particles are fermions, or the Bose-Einstein distributions if the particles are bosons. So this Hamiltonian is actually generic for free fermions or free bosons. Okay? Suppose that we are considering just such a simple free electrons or free phonon problems. And this is the Hamiltonian. And we evaluate this number operator, expression value of the number operator. So this gives us either the Fermi-Dirac or this Bose-Einstein distributions functions, and the problem is solved. Because the Hamiltonian, if I take the expression value of this Hamiltonian, it is nothing but this, right? A dagger K, A K, take an expression value, right? But what is this? This is nothing but n of k, right? So this is nothing but n of k. Therefore, your expression value of the total energy is nothing but sum over k, epsilon k minus mu, n of k. That's it. And you know what nk is, because nk is either Fermi-Dirac or Bose-Einstein. If you don't use that occupation number or this kind of operator, it's not that straightforward to actually calculate this expression value of the total energy. But if you use that second quantized fields, it is just a piece of cake because you already know the Fermi-Dirac and Bose-Einstein, and the only thing you need to know is to count the particle number, and you know the particle number, and you know everything. Suppose it's just a free non-interacting electrons or bosons, then the problem is solved by using second quantization formalism. And even in the presence of an interaction, say Coulomb interaction, and this quantization formula, second quantized fields are also very useful because we could actually rewrite this Hamiltonian by using some approximations and to the operators, which is also a function of the number operator, n of k. So the lesson is that no matter how difficult the problem is, we can always try to reduce the Hamiltonian to the operators, which contains the number operators. Okay, remember that Hamiltonian operator is a function of a number operator, and we know how to deal with number operator because we already know this. Therefore, the problem is solved, approximately solved. This is the key. We don't use the second quantization, and for the more complicated interacting system with a messy Hamiltonian and messy potential energy, and we have no idea. We have no way to do any calculation. But with the help of the second quantized fields, we are able to do something. Under some approximations, this problem can be computed or can be addressed. And this is the only way that we can address many-body problem is that by using second quantization. So this is a complete answer to my earlier proposed questions. What we get, what's the benefit to use second quantization formalism? Well, this is the benefit. Otherwise, we cannot do anything, almost anything. I guess that's probably good enough for today. So let me just stop here for your questions. And we haven't calculated the Coulomb energy for two-body interactions, okay? But we will do that on Wednesday. Okay? So now we are equipped to do real calculations for a real, solid-state problems. After all, so try to study by reading our textbooks and all the references, say David Pines and also Fensberg, and do the homeworks and think about this problem. Okay.